So now that we have spent a bit of time talking about the GameNode class, in this video we shall be coding it up. So we're turning our attention over to our game folder once again, because this class deals more with the descriptions of game items as opposed to engine type functionality. So let's go ahead, Logan, and create the base class itself, our GameNode class.
All right, let's jump down into the game folder, and we'll add a new item. This, of course, will be our GameNode. GameNode and add. Alright, two things to clean up before we get into the code itself. The first of those is to strip off the sub namespace and add in a using statement. And this using statement will be for Microsoft XNA framework.
Excellent. Now we can go ahead and make sure that GameNode extends node.
Because it is in fact a node, we would very much like to leverage all the graph and hierarchical abilities, the positional abilities, and so forth that comes from node.
And go ahead and build real quick.
If we were to build, you'll notice that we have a build error. It's saying that there is no overload for the nodes constructor that takes in 0 arguments.
That's right, because if you guys recall, the node constructor took in a sprite sheet. So in a few minutes after we've created a couple of our fields, we will create a constructor here that's going to take in a sprite sheet, and then we'll turn around and we'll pass that to the base.
But before we get to that, we need to drop in our fields. Those fields are going to be for managing health and our collision list, both of which will be public. The health will be an integer, so we'll get that dropped in. Second, we'll have a public list of type GameNode, and we'll call this the collision list. And once again, it's this collision list that allows us to configure which items or which other game nodes this specific game node will collide with. Meaning that if this brand new game node is actually an enemy, well, his job is to collide with players. If this new game node is a projectile, well, his job is to collide with enemies. So there's 2 different lists that each of the 2 different nodes would be assigned to. So this collision list system really does allow us to give collision grouping ability.
Okay.
Alright, moving on, now we can go and drop in a constructor for GameNode that satisfies the base constructor's need for a sprite sheet. This will be a public constructor, so we'll drop in GameNode. We need to take in a sprite sheet. We'll simply call it sprite sheet. And we will chain this to the base constructor. And to that base constructor we can now pass along the sprite sheet. And there's no further code that I need to have happen on creation of a game node, so I'm simply going to leave empty braces off to the side. Alright, moving on, now we can start addressing the collision code for a game node, and this is actually going to start in update. Now, because of the fact that these methods are interconnected, update is going to rely on another method called collide, I'm going to go ahead and just drop all the methods in place. And after we get the skeleton in, we can go back and link everything up.
Sure.
So we will know that we're going to override update. So overriding update from node. And let's see. We're going to have a virtual method called collide. Public virtual void collide. Collide is going to take in a game node called node. And I'm actually going to leave the braces off to the side because collide isn't going to have any implementation inside of GameNode. It is meant to be used later in other game nodes when they need to be notified of the fact that a collision has occurred. After this, we'll have another virtual method. This will be a public virtual void take damage. And take damage is going to take in an integer for the amount of damage. And finally, we have 2 more methods. These methods will be used to make it easier to remove items out of the game that have fallen off the edge of the screen. Since your area of gameplay is based on the screen itself, if you have enemies that have slid past you and are now off screen, those need to go away. We don't want to leave them in the list. If you've had projectiles that have missed enemies and gone off the top of the screen, we want those removed from the game as well so we don't have an infinitely growing number of items in the game. So we're going to create 2 methods that will allow us to handle things as they go off screen. The first of which will be a virtual method, public virtual void remove off screen. and we'll have another method that performs the actual work of removing things, and this is going to be called remove out of bounds. It'll be a public void method, and let's see, remove out of bounds. And remove out of bounds is going to take in a rectangle to describe the bounds that should be considered for removal.
Nice.
All right, now that we have the skeleton in place, we can go back up to update and get our collision system put together. Now you may be wondering, you thought we had said back in Node that the collision system is done because we had acquired the entire thing from passcode in our old actor example. Well, we have the collision system in the sense that we can check a collision between any two nodes. But that's where the abilities of that system stop. We can only compare nodes two at a time.
Node A and Node B.
Exactly. So here we're running into a scenario where we need node A against this group of nodes. So we're going to put a loop into update to accomplish just that. This loop will be able to say, all right, node A is us. Node B's are all of the nodes in our collision list. So we need to have a loop that will consider all of the nodes in the collision list and check them one by one to see if they have collided with us. If that is the case, then we'll actually make a call to this collide virtual method. And even though nothing happens inside of node, that means in later nodes, if we override the collide method, we don't ever have to worry about how that our node A versus all of the node B's work. That just suddenly becomes a black box, and all we know that, we collide with, say, enemies. And later in time, we have collided with something. What have we collided with?
With this particular enemy.
Exactly, given as that specific game node. So, to put this into action, the first thing we need to do before we check all of the node B's, all of the items in the collision list, we should first make sure that that collision list is not null. You'll notice the fact that we have not initialized the collision list up here in the fields, and we have not initialized it in the constructor. Unless set from outside of the game node, it remains uninitialized, remains null. And the reason being is, well, that actually makes it relatively easy to make a specific game node that just doesn't collide. You don't set up a collision list, he doesn't check anyone for collision. So we need to make sure that that is set beforehand. So if this dot collision list is not equal to null, then we know that we do have some nodes that need to be considered for collision. So I'm going to set up a scenario where we can loop backwards through that collision list and see if collisions have occurred. So I'll set up a reversed for loop that begins at the end of the collision list, which would be collision list.count -1. And then for each node, we're going to check and see if, well, the check on collision detection, as a matter of fact, let me put a little bit more of this in and I'll explain it. If node.checkCollision, this check collision being the functionality that we gathered from the original actor.
Yeah, basically when we were coding up the node class just a couple videos back, we jumped over and we copied the old code.
As a matter of fact, that was the entire collision code region that we grabbed.
Exactly, which contained this guy right here.
It contained check collision, and if we look at its method signature, we need two nodes, a node A and a node B. And as I mentioned earlier, node A is always going to be us. So we can put in this for node A. Node B is going to be all of the, as I termed, node B's in the collision list. But since we're walking through them one by one, that would be collision list sub I. So this dot collision list sub I. That should get that specific game element out and test it for collision. So if there is in fact a collision between ourselves and one of these other items in the collision list, we'll make a call out to this dot collide. And then we'll pass in the node that was collided with, or this dot collision list sub I.
Which gives us the node we collided with.
Exactly. So that goes down to this yet to be implemented method, but that can be implemented later in some other class, and then we never have to worry about this block of code ever again. That becomes a black box existing inside of GameNode. And really, that's pretty much it. I think that really is it for the collision system now.
Yeah.
We've got the base code that does per pixel checks on node to node, and now we've got this enhanced system that can do one node to many nodes. So we'll later leverage that functionality through the use of setting a collision list as, you can almost say, our input, and then waiting for calls to collide as our output, where GameNode itself acts as a black box. Alright, now we can move on and we can address the take damage method. Really, the whole point of take damage is just to make our health go down, because that's the key thing that happens. The reason it's being put in place as a method is so that we can have other things happen. So we'll use take damage as an action that occurs, not just a value that changes. This makes it so that as we take damage, we're given the opportunity to do checks, because if our health is gone 0 or negative, then we have died and need to be removed from the game. So the first thing to do is to accomplish the value change, that is changing the health and decrementing it by however much damage was done by the amount. Then we can check the health and see if we've died yet. So we'll say if this dot health is less than or equal to 0, then we have died. If we have died, we will remove ourselves from the game. So this dot remove. And you'll notice I'm hesitant to say remove ourselves from the main list, because really remove marks us as dead, and then later we get removed out of the list by the cleanup method.
That's right.
And moving on from here, I'll also note that we will be coming back to take damage at a later time as we enhance GameNode to handle things like exploding objects, but we'll worry about that as we get to it. For now, it's simply used to manage health and dying. Alright, moving on, the last two methods, we need to consider off-screen removal. Once again, we want some way to be able to, one, remove things that are outside of a rectangle. Basically, the way remove out of bounds. As a matter of fact, I'm going to do remove out of bounds first, because that one is more simplistic in nature.
Okay.
As a matter of fact, I'm going to code it out, as that'll make it easier to give a little bit of a visual. The way this is going to work is we're going to say that if not bounds dot contains, and contains takes in several overloads, I'm actually going to use one of the overloads that allows us to specify 2 integers. Reason being is that was the closest thing I could find to a vector 2, because right now a point is represented by our position as a game node, and our position is as a vector 2. The easiest way we can get that into the rectangle contains is just to take the x and y component and cast them to int, because we would have to do that anyway if we were trying to formulate a point. So we'll take the int casted result of this dot position dot x and the int casted result of this dot position dot y. That assembles the point in form of x, y fed to contains, and if that's the case, then we need to remove ourselves. Now, an explanation of what's going on here is remove out of bounds will be called as a check. Even though it sounds like that's going to accomplish something, really it could almost be called check remove out of bounds, because what it is going to do is it's first going to check the given bounds as a rectangle. So check the given rectangle against our position, us being a game node, and see if we are not in bounds. So let's describe bounds as the screen itself. If we are not contained within the screen, we must be off-screen. If we're off-screen, we'll get removed. So that's how this works. And bounds is being fed in, so that remove out of bounds could be arbitrary. That means maybe certain nodes are taken out of play immediately off-screen. Maybe some nodes can actually circle back around and come back on-screen. In that case, we need a larger bounds area so we don't get clipped the moment we touch the edge of the screen.
And that's something that we're going to have to take into consideration up in the remove off-screen method. Because right now, if you think about the way the remove out of bounds works, the bounds that comes in, if that's just representing our screen and we're dealing with just a point, seeing if that point is inside that rectangle, at the moment the point is out, we could still have some of the thickness because the origin of that particular sprite is going to be at the center. And so that point may have just gone out of screen, but part of it could still be in the screen and it would just pop out of existence.
Ah, so we're actually going to have to work with the screen dimensions a little bit to make sure we don't get any popping because we're center or origin around the center.
Exactly, and that's what we're going to do here in the remove off screen.
And another way to look at remove off screen is it's almost like a preset for remove out of bounds so that we don't have to externally to GameNode always have to formulate the screen area and then feed that over. It would be a lot more convenient to say just, all right, us as a descendant of GameNode, make sure we're not off screen, and if we are, remove. And then what really happens is, okay, we figure out our own dimensions, the screen's dimensions, make sure everything's wide enough, and then make an internal call to remove out of bounds.
Yep.
So the first thing we need to do is to establish, well, what rectangle would describe the screen bounds. So I'll make a rectangle variable, and we'll call this bounds. and we'll make a new rectangle with dimensions 0 by 0, which would in this case represent the top left-hand corner of the screen, and we'll give the width and height as the dimensions of the screen. Screen width and screen height being held in config means we can access config.screenWidth and config.screenHeight. So we'll feed those in, and now we have formed a rectangle. Now, like you were just saying, if we use this rectangle directly, then we'll have problems where we'll still be able to see half of any of the given items as they actually disappear. And to prevent that, what we'll do is we'll take the screen bounds and we'll actually say, let's expand the allowable playable area to actually a little bit bigger than the visible range of the screen. And the amount that we'll extend it to is just enough to make sure that we're completely off screen before we get destroyed. So what is just enough? Well, just enough is to make sure that our origin plus the edge of ourselves is off screen. An example is an asteroid is 64 by 64 pixels. That means its origin is at 32 by 32. That means we want to make sure we go a full 32 units off screen before we get removed.
Right. In reference to the origin, the point.
Exactly.
Which means now all of that particular sprite is off screen. So we'll simply inflate our rectangle now.
Exactly, because in order to do that, you got to keep in mind that, well, it's not just 32 on one edge, it's 32 top, bottom, left, and right.
That's right.
So we actually need to take all four edges of the rectangle and move them outward by the origin pixel, so 32 in this example. Fortunately, there is an inflate method that's part of the rectangle type that allows you to do just that. Specify an amount in X that you'd like to inflate, an amount in Y that you'd like to inflate, and the entire rectangle will inflate with all edges extending outwards. So we'll take our bounds rectangle and we will tell it to inflate, and we'll give it a horizontal amount of our sprite's origin X. So this dot sprite dot origin dot X. Now you will note that the X component of a vector is float, and our rectangle is taking in an integer. So once we obtain this, we need to cast it over to an integer. And we'll do the exact same thing for Y. As a matter of fact, I feel lazy at the moment, so I'm going to copy the value we obtained in X. So we have the int casted sprite.origin.y for a vertical amount. So once we inflate the bounds rectangle, now we have a little bit of off-screen space to play with so that our node can make it all the way off-screen visibly before it disappears. Now that we have a rectangle that we can use, we'll just make a call to remove out of bounds using the rectangle. So this dot remove out of bounds, and we'll feed in bounds as the rectangle. So what's cool here is, one, we have a high flexibility way of calling remove out of bounds and performing the remove action, and two, we have a lower flexibility but easy to call method named remove off screen. So that way, if we don't care about any special abilities, like we don't want to be able to fly far off screen and come back, we can just call remove off screen and forget about it. If we want a more complex scenario where we want to be able to fly off screen, then we can override remove off screen or even change how update is working, and then either use both or any one of them in any conjunction to come up with a good idea for what bounds should be considered.
And this will allow things like seeking missiles that are flying off screen, but they're in the middle of changing their trajectory so that they're going to come back around to attack their target. This allows for them to go off screen and come back on.
Exactly, and it makes it to where only in an overridden case like that will that happen. That means we don't have to have this massive amount of external screen space for everything, so we don't have thousands of asteroids that are just sitting out there in extensive space. Asteroids never come back on screen. They can get clipped immediately.
Right.
But like you said, in the case of a missile, we'll give them more leeway.
Exactly. And with that, let's go ahead and build, make sure everything builds fine. Just a few warnings, and that's going to wrap up this video. Thanks a lot, everyone.